Imagine needing to slice through a thick piece of metal. You might think of a powerful saw or maybe a screaming grinder, but what if the best way, the most effective way, involved a carefully controlled chemical reaction? Or maybe a superheated jet of gas, or even just compressed air.
That's exactly what we're diving into today. We're exploring the world of thermal cutting processes. You sent over some really great technical material covering everything from, the classic oxy-fuel flame right up to high-tech plasma arcs and even some specialized gouging methods.
Yeah, and our mission here is to unpack how these different techniques actually work. What are their unique strengths? What are the limitations, sometimes surprising ones? And, crucially, why choosing the right method is so important. So get ready to really understand what's going on when metal meets extreme heat.
And we're drawing this all from a pretty detailed technical document covering these various processes. So solid ground here.
Okay, let's kick off with the fiery classic, Oxy-Fuel Cutting. It really is a marvel of controlled chemistry, isn't it? It's not just about melting metal. It's much more specific.
Precisely. You're spot on. This process cuts or removes metal by really leveraging that chemical reaction between oxygen and the metal, but only at high temperatures. So first step uses a preheating flame.
That's usually oxygen and a fuel gas mixed together.
Right, like acetylene or propane.
Hmm.
That flame brings the metal, let's say steel, up to its ignition temperature, which is around 850 degrees Celsius.
Okay, hot enough to ignite.
Exactly. Once it hits that temperature, then you unleash a stream of pure oxygen through the center of the quartz tip. This oxygen rapidly oxidizes the hot metal, basically. It makes it rust very, very quickly.
And that oxygen stream does more than just react, right?
Yeah, the kinetic energy, the force of that oxygen stream physically blows away these molten oxides and any other liquid metal that's formed. And that action creates the cut, or the kerf, as it's called.
So it reacts, then blasts the gunk away. But you mentioned it's specific. What are the sort of Goldilocks conditions? What does a material have to do for this to work well?
Right, this is key. There are two critical conditions. First, the metal's ignition temperature, where it starts burning in oxygen, must be below its own melting point. If it melts before it burns, you just get a puddle.
Makes sense. Burn first, melt later. What's the second?
The second condition is about the oxides, the ash from the burning metal. The melting temperature of those oxides also has to be below the melting point of the parent metal.
Ah, so the rust has to melt easily too.
Exactly. If the oxides don't melt and become fluid at the cutting temperature, they can form a sort of crust, blocking the oxygen jet from reaching fresh metal below. So you need the metal to burn before it melts, and its oxides need to melt easily and get blown away. If either isn't true, oxy-fuel cutting just won't work properly.
That really clarifies why it's not universal, and it explains why it's mainly limited to things like carbon steels and low alloy steels, doesn't it?
It does. The issue is alloying elements. Things like aluminum, chromium, sometimes nickel or manganese. Their oxides often have much higher melting points than iron oxides. They're refractory, meaning heat resistant.
So they form that crust you mentioned.
Pretty much. These refractory oxides can build up in the cut, shield the metal underneath, and stop that continuous clean oxidation reaction. It makes the cut unstable, slow, or might even stop it completely.
So there are practical limits on how much alloy content you can have.
Yeah, generally you're looking at steels with less than about 0.25% carbon, maybe less than 5% chromium, and low levels of other elements like molybdenum or manganese. Push beyond those rough limits, and oxy-fuel cutting gets really tricky or just impossible without special techniques.
Okay, so very specific chemistry needed. But even with those limits, oxy-fuel is still a workhorse. It must have some real advantages.
Oh, absolutely. Huge advantages in the right context. For starters, you can cut steels much faster than with most machining methods, especially thick sections.
Faster than sawing or milling.
Often, yes. And it's economical for cutting complex shapes or thick plates that would be really difficult or expensive to handle mechanically. The equipment itself, well, the basic manual setup is relatively low cost.
Compared to big machine tools, I bet.
Definitely. And that manual gear is super portable, perfect for on-site repairs or fabrication. You can easily change cutting direction, cut big plates without needing massive machinery to move the plate itself. You just move the torch. And it's great for preparing plate edges for welding.
High portability, low entry cost, good for bigger, simpler stuff. Makes sense. But there are always trade-offs. What are the downsides we need to keep in mind?
Well, the first is precision. Your dimensional tolerances are just not going to be as tight as what you'd get from a machine tool. It's a rougher cut, relatively speaking.
Okay, so not for high precision final parts.
Generally, not without secondary finishing. And as we just discussed, it's basically limited to carbon and low alloy steels. Then there are the safety hazards. You've got an open flame, flying sparks, red-hot molten slag. Fire and burn risks are real.
Plus fumes, I imagine.
Yes, you need good fume extraction and ventilation. You're burning fuel gas and oxidizing metal, so that creates fumes. Also, for some steels, the heat can harden the edges of the cut.
Hardenable steels.
Right. Those might need preheating before cutting or post-heating afterwards to control the metal structure and prevent cracking.
Yeah.
And if you do try to cut high-alloy steels or cast irons, you need special tricks, like injecting iron powder or flux into the stream to help the reaction.
Ah, okay. That's complex.
And don't forget the basic physics of heat, thermal expansion when you cut, and shrinkage as it cools. You have to account for potential distortion.
It really sounds like the gases themselves, the breath of the flame, are critical. Let's talk oxygen purity first. You mentioned pure oxygen. How pure does it need to be?
Extremely pure. Ideally 99.5% or higher. It's critical for efficiency.
What happens if it's less pure, say at 98%?
Your cutting speed drops dramatically. You use way more oxygen for the same cut. Efficiency tanks if it drops below, say, 95% purity. Cutting basically stops working properly. It becomes more like a messy melt and wash action where you're just melting the metal rather than getting that clean oxidizing cut.
Wow, okay, so purity is not negotiable. What about the preheat flame? You said it gets the metal hot, but does it do anything else?
It does. It's surprisingly multi-talented. Obviously, number one is raising the temperature to ignition point, but also keeps supplying heat during the cut to maintain the reaction, especially on thicker material or rusty surfaces.
Ah, helps keep it going.
Yeah, and it provides a sort of protective shield, displacing atmosphere around the oxygen jet, preventing contamination, and it can even help dislodge light rust or paint ahead of the cut.
So it cleans the path, too. That's interesting. Given all that, choosing the fuel gas for that preheat flame, probably not just about cost.
Definitely not. It's a strategic choice. You consider things like how fast it preheats time is money, how it affects the maximum cutting speed, the cost and availability of the gas, sure, but also how much oxygen it needs to burn efficiently for a neutral flame, and, of course, safety in handling and storage.
What are the common choices? You mentioned acetylene and propane.
Those are big ones. Acetylene gives the hottest flame very focused, great for rapid preheating, especially on thinner plates or doing double cuts. Propane has a lower flame temperature, but a higher total heat content, spread out a bit more.
So propane's better for?
Often better for thicker sections, say over 100 millimeters, or for machine cutting long, straight lines where that intense preheat isn't as critical. There's also MAPP gas, sort of intermediate temperature, sometimes used for underwater cutting. And gases like propylene, natural gas, or methane are also used, often for specific applications based on local cost and availability, typically machine cutting thicker stuff.
Okay, lots of factors. So let's picture the cut itself. What does a good oxy-fuel cut look like? And how can you tell if something's gone wrong just by looking?
A good cut has distinct characteristics. You want a sharp top edge, not rounded or melted over. The cut face should show fine, vertical, or slightly lagging drag lines. Those are the ripples you see. You want minimal, tightly adhering oxide scale. The bottom edge should also be sharp, and importantly, there should be little to no slag, that resolidified molten material, sticking underneath.
And the cut itself, the kerf.
Typically, the kerf width is relatively large with oxy-fuel, usually over 2 millimeters. Roughness should be fairly low, maybe under 50 micrometers raw, which is actually pretty smooth for a thermal cut. Edge squareness, how perpendicular the cut face is to the plate surface, is okay, but not perfect, maybe deviating by 0.7 millimeters or more over the thickness. And there's always a heat-affected zone, the HAZ, where the metal structure changed due to heat, ideally kept narrow, maybe around a millimeter or so.
Right, so what are the visual clues if things aren't right? What if the operator's going too slow?
Yeah, the signs are pretty clear then. If you're moving too slowly, the top edge will likely be melted and rounded over significantly. You'll see deep grooves running down the cut face, maybe some heavy scaling, and the bottom edge will often be rough with a lot of dross. That's the slag, stubbornly clinging on.
Okay, melted top, deep grooves, clingy dross. What about too fast?
Too fast looks different. The cut edge itself might be irregular, not a clean line. The drag lines become coarse and angled quite sharply backward, showing the oxygen jet isn't penetrating effectively all the way through, and you'll often get excessive slag sticking to the bottom edge because the reaction isn't completing properly at the bottom.
Even the preheat flame matters visually, you said. Too low.
If the preheat is too weak, you might get deep gouges starting partway down the cut face where the reaction keeps stalling and restarting.
And too high.
Too much preheat melts that top edge excessively again. The cut face can become irregular, and you might get more adherent dross. Even things like the nozzle height matter. Too high off the plate, you melt the top edge. Irregular travel speed. You'll see unevenly spaced drag lines and an uneven bottom surface. It really shows how technique and setup are crucial.
Definitely a process that requires skill. Okay, so Oxy-Fuel. A fiery classic, great for steels, portable, economical for many jobs, but with chemical limits and needing careful control. What if you need to cut stainless steel, or aluminum, or even something non-conductive? That chemistry just won't work. We need a different approach.
Exactly. And that often leads us to plasma arc cutting, the electrified stream.
How does plasma cutting work? It sounds high-tech.
It is, sort of. It uses a constricted electric arc and a high-velocity jet of ionized gas, that's the plasma, to melt and physically blow away the metal.
Ionized gas, like lightning in a bottle.
Kinda. You start with a pilot arc, a small arc struck inside the torch itself, between the electrode and the nozzle. Then when you bring the torch close to the workpiece, this arc transfers to the metal you want to cut. The key is that the arc is forced through a small orifice or nozzle.
Constricting it.
Right. That constriction dramatically increases the temperature and the velocity of the plasma gas flowing through it. This superheated high-speed plasma jet hits the workpiece, melts it instantly, and the sheer velocity blasts the molten metal out of the curve.
And that works on more materials.
Yes, this is the huge advantage.
Yeah.
Because it's primarily a melting and physical removal process, not a chemical reaction like oxy-fuel. It's not really limited by the material's chemistry in the same way. It works fantastic on stainless steels, aluminum, copper, brass, basically any conductive metal.
What about non-conductive? You mentioned that earlier.
Yes. There's a variation called the non-transferred arc method. In that case, the main arc stays inside the torch, between the electrode and the nozzle. The hot plasma gas itself is then expelled out towards the workpiece. It's less efficient, but it can be used to cut non-conductive materials like some ceramics or composites, though that's more specialized. Mostly, we talk about the transferred arc for metals.
So huge material freedom compared to oxy-fuel. That's a big deal. What about speed?
Much faster. Plasma operates at a significantly higher energy density. The temperatures in the arc are extreme, tens of thousands of degrees Celsius. This means much faster cutting speeds are possible, especially on thinner to medium thickness materials.
And no preheating.
Correct. Another major plus, instant startup. You pull the trigger, the arc transfers, and you're cutting immediately. This is really beneficial for things like cutting mesh or doing interrupted cuts where you're starting and stopping a lot. No waiting for preheat each time.
Okay, sounds great. Faster, more versatile, but new process, new risks, or maybe some of the same old thermal process issues?
Both, really. Plasma introduces a significant electrical shock hazard because the open circuit voltages are much higher than typical welding. The arc is incredibly bright, so proper eye protection against intense UV and visible light is absolutely essential. And it's noisy, much louder than oxy-fuel.
So electricity, bright light, noise, any mitigation.
Interestingly, doing plasma cutting underwater, which is common in some industries, significantly reduces the fumes, the UV radiation, and the noise level. So that's one approach.
Underwater cutting. Fascinating. Downsides besides the immediate hazards.
Well, the equipment is generally more expensive than basic oxy-fuel setups, and it needs a hefty electrical power supply, which might not always be available on site. And yes, like any thermal process, you still have to deal with thermal expansion and contraction causing potential distortion. Also, plasma cuts typically have a slight bevel or taper on the edge, more noticeable on thicker materials.
Okay, so plasma gives speed and material versatility, but costs more, needs more power, and has its own set of hazards. Now, what about gouging? You mentioned specialized methods. Let's talk arc air gouging. That sounds aggressive, using compressed air.
It is pretty effective. Arc air gouging, sometimes called air carbon arc gouging, is a bit different. It's less about making a narrow cut through the material and more about removing material from the surface, creating a groove or a bevel.
How does it work? Arc and air.
Basically, yes. You strike an electric arc between a special carbon electrode, usually coated in copper for better conductivity, and the workpiece. This arc melts the metal, just like in welding. But then, the torch has jets aimed right along the electrode, blasting compressed air at high velocity.
And the air just blows the molten metal away.
Exactly. The air jet physically removes the molten pool created by the arc, leaving behind a groove. The torch itself is designed specifically for this, holding the electrode and directing the airstream precisely. You hook it up to a standard welding power source and a compressed air line.
Does the air pressure need to be super precise?
Not really, which is handy. Usually, standard shop air pressure is fine, maybe 80 to 100 psi. You don't typically need a special regulator just for the gouging torch.
So what's it used for mainly? Removing welds, preparing edges?
All of the above. It's very common for back gouging welds, removing the root of a weld from the backside to ensure full penetration when welding from the other side. It's used to remove defective welds, prepare cracks for repair by grooving them out, and create bevels or specific edge preparations on plates before welding, often U-shaped or J-shaped grooves.
And material-wise, like
So
plasma.
the big plus is that it works on almost any metal that conducts electricity: steels, stainless steels, cast irons, nickel alloys, copper, aluminum. It's just melting and blowing away.
Sounds efficient. What are the main advantages?
It's incredibly fast compared to mechanical methods like chipping or grinding for removing bulk material, maybe 5 times faster than chipping, sometimes more. You can see what you're doing clearly, making it easy to follow a crack or remove just a specific defect.
Precise control, then.
Yeah, the depth of the gouge is pretty easy to regulate by changing travel speed, angle, and current. Slag from welding doesn't really interfere with it. Equipment costs are relatively low if you already have a suitable welding power source. You just need the torch and electrodes. No gas cylinders needed on site, just compressed air.
So economical, too.
Right. No oxygen or fuel gas costs. And it's fairly easy to learn. Similar skills to stick welding,
Yeah.
MMA. Plus, the torch is compact, good for getting into tight spots. It can even be automated.
Okay, fast, versatile, economical, easy to use. Sounds almost too good. There has to be a catch. What's the big drawback?
There is one major one: carbon pickup. Because you're using a carbon electrode, some carbon inevitably gets transferred into the molten metal surface of the gouge.
And that's bad.
It can be very bad, depending on the metal. In cast irons or hardenable steels, this extra carbon increases the hardness of the gouge surface significantly, potentially making it brittle or difficult to machine.
What about stainless steel?
That's where it's particularly problematic. The carbon pickup in stainless steels can lead to something called sensitization. Basically, chromium carbides form along the grain boundaries in the heat-affected zone.
And that reduces corrosion resistance.
Exactly. It depletes chromium near the boundaries, making the stainless steel much more susceptible to certain types of corrosion. So if you arc air gouge stainless steel, you almost always must grind the surface afterwards to remove that carbon-rich sensitized layer before welding or putting it into service.
Okay, that's a critical point. So grinding is often a required follow-up step, especially for stainless.
Yeah.
Any other hazards?
The usual suspects for high-energy processes: lots of sparks and molten metal flying around, so fire risk is high.
Yeah.
Significant fumes are generated, it's noisy, and the arc is extremely bright, requiring proper PPE.
Right. Familiar thermal process hazards. Okay, one more method mentioned in the material. Manual metal arc gouging. This sounds like using a standard welding setup somehow.
Sort of. It uses the same power source as manual metal arc welding, or stick welding, but with a special type of electrode. These gouging electrodes have a very thick flux coating,
Thicker than a normal welding rod's coating.
much thicker. When the arc is struck, this heavy flux coating burns and produces a large volume of gas. Unlike welding, where you want a controlled gas shield to protect a stable weld pool, here the idea is that the forceful gas evolution physically ejects the molten metal from the arc zone.
So the flux gas does the blowing instead of compressed air.
Precisely. The arc melts the metal, and the expanding gas from the flux pushes it out of the way, creating the gouge.
How does the quality compare to arc air gouging or even oxy-fuel? Smoother, rougher?
Generally, the surface finish isn't quite as smooth. The gas stream generated by the flux isn't usually as powerful or directed as the compressed air jet in arc air gouging, or even the oxygen jet in oxy-fuel cutting, so the resulting gouge can be a bit rougher.
So why use it then? What's its niche?
Convenience, mostly.
Yeah.
Its main application is for small, localized gouging jobs. Think removing a small surface defect or a quick bit of back gouging, especially in situations where a welder is already stick welding. It's often easier for them to just switch from a welding electrode to a gouging electrode for a moment, rather than setting up a separate arc air gouging torch and airline.
So a quick fix using the existing setup?
Exactly. It avoids needing extra equipment for occasional minor gouging tasks.
But you probably trade off something for that convenience.
You do. The metal removal rates are typically lower than with arc air gouging. And it's mentioned, the surface quality isn't usually as good.
Does it have the same carbon pickup issue as arc air gouging?
Generally less so, but it can still happen, especially with stainless steel. While for many general carbon steel applications, you might be able to weld directly over the MMA gouge surface without grinding, for stainless steel, that same caution applies. You will likely get some carbon pickup, creating a thin layer that really must be removed by grinding to restore the corrosion resistance.
Okay, so convenience for small jobs, but lower performance and still need to be careful with stainless. Got it.
That covers the main ones we looked at.
So we've really journeyed through quite distinct worlds of thermal cutting, haven't we? We started with oxy-fuel, relying on that specific chemical reaction, the fiery classic, then moved to the sheer power and versatility of the plasma arc's electrified stream, and finally looked at the specialized force of arc gouging, either blowing molten metal away with compressed air or using that heavy flux action.
Yeah, and each one, with its own physics, its own chemistry, its unique set of advantages and disadvantages, really carves out its own specific place in industry.
And tying this all together, I think for you listening, understanding these differences, these nuances, it really drives home that cutting metal isn't just about applying brute force heat. It's actually a very strategic decision.
Absolutely. It's influenced by, well, obviously the material you're cutting, but also the precision you need, the thickness, your budget, site conditions, and crucially, always thinking about the safety aspects involved.
It's about knowing when that classic oxy-fuel flame is the perfect tool, maybe for thick carbon steel plate on a construction site. Or when you really need that electrified plasma stream to tackle, say, stainless steel or aluminum, something the flame just can't handle effectively.
Right. Or when you need to quickly remove a weld defect, and arc air gouging is the fastest way, excepting you might need to grind afterwards, choosing the right tool for the job.
So this brings us to a final thought, maybe something to ponder. As we keep developing new materials, think about advanced alloys, composites, materials with really complex properties we haven't even fully characterized yet. How do you think these thermal cutting technologies will need to adapt?
That's a great question. Will we see refinements of plasma? Maybe new gas combinations? Or will the challenges posed by tomorrow's advanced materials push us towards completely different methods? Perhaps laser cutting becomes more dominant, or maybe even more exotic processes we haven't widely adopted yet.
Or perhaps entirely new ways of using controlled heat or energy that we haven't even invented. It really makes you think about the future of making things.